Hi, my name is Brooke. I'm an assistant professor at Kennesaw State University. I'm happy to present our work, How Spatial Ability Affects Responses to Gaze Adaptive Cueing and Mixed Reality Spatial Navigation. Mixed reality hardware display can seamlessly overlay annotations such as landmarks and points of interest directly onto the environment and provide tools like word imagery maps within the user's field of view for supporting navigation. Information cues in these systems are typically selected based on geospatial location proximity and relevance to the task goal. These geospatial triggered cues function as external stimuli, automatically providing information based on physical proximity regardless of whether users are consciously focusing on them. However, individual differences in attention engagement and spatial information processing pose challenges for this type of cue display mode. Users with varying spatial ability and prior knowledge may exhibit distinct attention pattern and utilize cues in different ways. As eye tracking technology has been integrated as a standard module in mainstream commercial mixed reality head-mounted displays, gaze adaptive interfaces are increasingly employed in mixed reality to support attention-aware interaction. Previous research showed that gaze adaptive interfaces improve performance and user experience, such as visual search among points of interest in the surroundings and accessing personal application information. Despite increasing interest in gaze adaptive mixed reality system, little is known about how gaze adaptive information display influence user dynamic attention and spatial learning during navigation, and whether these adaptations adds cognitive load, especially for users who struggle with spatial navigation and wayfinding tasks. The study proposed a navigation interface that integrates both proximity triggered and gaze adaptive cue. The gaze adaptive interface operates on the principle that when users draw on target landmark, either in the environment or on a word imagery map, a virtual cue is triggered on both, really reinforcing their spatial correspondence. Targets within the map display range could be triggered by gaze. The design of this gaze adaptive cue is guided by three key considerations: temporal activation, spatial activation, and user feedback. For temporal activation, we ran a pilot study with 16 participants and determined to use the 200 millisecond SDO time for cue triggering. For the spatial activation, the form of the visual cue adjusts to the spatial relation of a target. When it is visible, the facets will be fully highlighted. When it is not visible, we adopted X-ray realization as approach of displaying occluded landmarks along with contour highlights as visual cues. Gaze trigger cues were deactivated either after lasting 4 seconds or after new dwell on a new object was detected, ensuring sufficient guidance without causing clustering or distraction. We compared the hybrid adaptation design, which combines the gaze adaptive and proximate triggered cueing, to proximate triggered only interface to determine if gaze adaptive components enhance navigation effectiveness. Specifically, we asked a research question here. How does the integration of gaze adaptive cue influence user gaze behavior, spatial learning, and cognitive load during mixed reality navigation? How do differences in spatial navigation ability modulate user response to gaze adaptive interfaces? A secondary goal of our paper is to provide evidence to advance the understanding of whether and how specific gaze metrics reflect spatial learning and spatial ability in the context of mixed reality spatial tasks. We link gaze pattern to self-reported spatial ability and spatial learning outcome in the experiment to explore the potential for content-independent gaze metric captured through eye tracking on current mixed reality head-mounted display. We hypothesize that individuals with higher spatial ability exhibit more structured and mindful eye movement behavior driven by top-down attention during spatial learning. We used a study to compare the two cue conditions with 60 participants. Prior to the experiment, participants began by completing the Santa Barbara Sense of Direction questionnaire to assess their navigation ability and the Similar Sickness questionnaire. Participants also practiced locomotion in a separate virtual environment. During the experiment, participants first completed an exploration task. They assisted with a assigned cue to navigate to a destination, memorize the position of 7 target landmarks, and responded to auditory stimuli and a secondary detection response task to measure the continuous cognitive load. Following exploration, participants completed 2 spatial memory tasks. In the pointing task, they were placed at one of 7 target landmark locations and asked to indicate the direction of the remaining landmarks. In the map drawing task, they placed landmarks on a virtual map and sketched the route they had taken. The tasks were designed to be conducted twice to gauge how user gaze behavior during navigation evolve with increased familiarity and whether any potential behavior changes occur when learning with different cues. Upon completing all tasks, participants completed the SSQ again. We measure gaze patterns during navigation by fixation duration, indicating how long users maintain attention on visual elements, reflecting depth of visual processing, and saccadic amplitude, capturing the visual angle between successive gaze fixation, indexing the breadth of visual exploration, and also gaze transition entropy, quantifying the randomness of gaze transitions with lower values indicating structured viewing pattern. We measure spatial learning performance by pointing arrow in the pointing task and map drawing accuracy reflecting configurational learning. And we measure cognitive load by the response time of the detection response task, with slower response time indicating higher attentional demand. For answering the first research question, data were analyzed with generalized linear mixed model. We focus on reporting the cue type, SBSOD score, and their interaction to answer the research question. For gaze behaviors, the results show that participants with higher SBSOD score exhibited longer fixation durations when including gaze adaptive cues. This may indicate more intentional engagement with gaze adaptive cues for users with higher spatial abilities. Regarding the general spatial learning outcomes, no significant effects were observed in the pointing task or the map drawing task with the integration of gaze adaptive cues in the navigation interface. We found no significant differences in DRT response time between navigation with and without gaze adaptive cues with generalized linear mixed model. And further Bayesian analysis suggests strong evidence for the null hypothesis, that is, there's no response time differences between the cue conditions than the alternative hypothesis. We summarize our findings regarding the first research question here. First, gaze adaptive cueing impacts users differently based on their spatial ability. Individuals with higher spatial ability engage with cue more and exhibited longer fixation. Second, the cue didn't measurably improve spatial learning, which may be due to limited exposure time and lack of explicit training with gaze adaptive system. This may have prevented participants, particularly those with lower spatial ability, from fully understanding or utilizing the adaptive cues. It can also be because of the settling effect of the baseline interface. Besides, the results suggest adding gaze adaptive elements triggered with a short dwell time does not negatively affect usability and cognitive load in the spatial navigation context, even if some users seem not to engage with them actively. Such systems are feasible for real-time application without impairing user attentional resources. To answer the second research question, we conducted Pearson correlations, examined the relationship among spatial ability, gaze measures, and spatial learning outcomes. The analysis was conducted on all data and among the variables for each cue type separately. Interestingly, we found that gaze behavior reflected individual differences in spatial ability, but the effect of spatial ability on gaze pattern emerged only when the system supported intentional gaze behavior via adaptive cues. Specifically, higher SBSOD score were associated with longer fixation duration, larger saccadic amplitude, and reduced gaze transition entropy, indicating more structured and intentional visual scanning. Second, we found that higher spatial amplitude correlates with better spatial learning performance in all data. This correlation is also observed in data when adding gaze adaptive cues for the pointing task. This suggests that broader visual scanning may contribute to more effective spatial encoding in gaze adaptive navigation interfaces. However, these relationships were not observed in the absence of gaze adaptive cues. Besides, notably under both cue situations, gaze transition entropy demonstrated a strong negative connection with fixation length. It demonstrates it permits a reliable metric for indexing structured and cautious viewer attention in mixed reality navigation tasks. We summarize the findings of the second exploratory question here. First, the results indicate that higher spatial ability correlated with more structured visual scanning when the system supported intentional gaze behavior via adaptive cues. Second, higher saccadic amplitudes was linked to better learning outcome, particularly when the adaptive cues were present. Third, gaze transition entropy showed promise as a content-independent obtrusive metric for structured and mindful viewer attention during mixed reality navigation and spatial learning tasks. Finally, we also provide implications on mixed reality design based on our findings. First, proximate trigger cues are a lightweight and effective solution, especially when computational resources are limited. Second, gaze adaptive cueing can be added to increase engagement for users with strong spatial skills, like first responders or experienced gamers. Third, designers must account for individual differences in spatial cognitive ability, as gaze adaptive system may inadvertently amplify existing disparities in spatial learning, favoring users with higher spatial ability while offering limited benefit to others. Fourth, the findings also suggest that evaluating gaze entropy as an indicator to quantify individual differences in spatial ability and cognition in mixed reality, advancing intelligent user profiling beyond the traditional psychometric tests. Finally, I'd like to thank my co-author and the Office of Naval Research to support the work, and thank you for listening. Feel free to contact me if you have any questions or thoughts.